Hey, Clay County. Today I've got a number one for you. It's going to be kind of down and dirty into the numbers here, and we're going to talk about this idea of a preferred planet, how preferred Earth is within the universe. And I'm going to deal with these numbers, these statistical probabilities, and the factors that are required for life to exist on a planet. And as we look out into the entire universe that we can observe, how likely are we to find a planet that already has life on it based on these different conditions? So bear with me. You're going to see this shrink really rapidly. To start off with, there's an estimated 100 trillion galaxies in the observable universe. There is an average of 100 million stars per galaxy. So that gives us a total of 100 quadrillion stars. That's 1 times 10 to the 17th, a 1 followed by 17 zeros. That's our starting point to count to allow for every star in the entire universe, as far as we can observe. And so we're going to go one by one through these factors, and we're going to start eliminating stars based on scientific estimations of each of these factors. So the first one that we want to talk about is the type of galaxy that we look at. For our purposes, we need to have a spiral galaxy that is circular, that has a pretty stable circular rotation, because if it's irregular in its rotation, then stars end up colliding all the time, and it's very unstable, very chaotic, and life is not going to be able to survive in that type of situation. And so it's estimated that 20% of the galaxies are elliptical or irregular, and so that drops us down to 80 quadrillion stars left. The next factor is the type of star. Supergiants are too large and too hot. Red giants are too large and too cold. Red dwarfs are too small and too cold, and would cause a planet to be tidally locked. That means one side of the planet would always face the star and the other side would always face away. Life can't exist in that situation. And we need a G-type yellow dwarf star because of radiation, because of its stability, because it's spherical, and a host of other factors. So we need a yellow star much like our own. And it's estimated that approximately 10% of stars in the universe are yellow stars. And so that drops us down to about 8 quadrillion stars. The next thing is we need our planet, whatever planet we're talking about, to be the right distance from the sun for water to exist. This is called the habitable zone, or the Goldilocks zone, because it's not too hot or too cold, so that water can exist in all 3 non-plasma phases on the surface. And the estimation is about 22% of stars contain planets that are in the habitable zone. This drops us down to 1.76 quadrillion planets or stars. And then within the galaxy, we need our planet or our star with a planet around it to exist between the arms, not in the arms, because they're denser and, again, more chaotic, a lot more energy, radiation, and just stuff flying around. And so we need to be in the relatively calm in between. And it's estimated that 40% of stars exist between those galactic arms if we're in a spiral galaxy. And so that drops us down to only 704 trillion stars. We're getting down into national debt area here. And then we also need in a galaxy to be located in kind of the middle distance between the center of the galaxy and the very edge of the galaxy. Because too far out and there's no heavy metals. The stars are all hydrogen and helium, and so we're not going to find any real habitable planets out there. There's just nothing but really light gases. And then too close to the center, it's way too much radiation, way too many stars packed in there. It's very dangerous. It's even more dangerous than being in the arm of the galaxy. And so we're right between 7 to 9 kiloparsecs. The galaxy is 30 kiloparsecs across, so right at the 7 to 9 from the center is where we want to be, and that's less than 4% of stars. And so that drops us down to 28.16 trillion stars left, and that's 1 star for every 4 galaxies in the universe. So we're less than 1 star per galaxy at this point. All right. The next thing is we need to have gas giants in the solar system. The gas giants not only need to be present, but they have to be relatively far from the star they orbit so that they can soak up all of the world killer objects that might come into the solar system, like really big comets and asteroids that might hit our planet. They can't be in the inner orbit because that doesn't help out anything. And less than 0.0001% of stars contain gas giants that are at the right distance. And so that drops us down from the trillions into the billions. We're at 28 billion stars. I'm sorry, that's not right. It's millions. Millions. I looked at it wrong. It's 28,160,000 stars left. That's one star for every 3.6 million galaxies. Then we have to have a planet that's the right size because of gravity. Too large, and the gravity would crush everything. No life would be able to exist. And too small, and you don't have an atmosphere. And Mars suffers from this. Mars is a little too small, and its atmosphere is so thin that we can't go there and exist on the surface right now. And so 49% of the planetary candidates that we've observed exist at the right size to support life, and that's estimating that everything that we've seen that is a candidate is actually a planet and not some kind of a dwarf star or other thing that threw our readings off. So 49% of the planetary candidates exist at the right size to support life, and that drops us down to 13,798,400 stars. That's one star for every 7.2 million galaxies that could support life. And then from there, we have to go on and we have to look at the planet itself. Does it have a stable orbit? Does it have a moon that's not too big or too small so that it has the engine of tidal forces to stir things up just enough so that life cycles can happen, all the different cycles on the planet that happen. A lot of that's because of the moon. The moon stabilizes the Earth's tilt. There's a lot of things that the moon does for us. It's got to actually have water on the surface. It's got to have an atmosphere. It can't have too much or too little radiation. It's got to have a metallic core so that it has a magnetic field surrounding it, protecting it from its solar winds. And then you've got to have oxygen cycle, sulfur cycle, carbon cycle, nitrogen cycle, phosphorus cycle, calcium, sodium, and so on. All of these things have to be going on the planet's surface. In fact, there's a total of more than 200 parameters for life. And each limiting factor that reduces the number from a few millions all the way down to way, way below zero. And what I mean by below zero in terms of that, you'll see here in just a minute. If we subtract out the factors we've already considered mathematically, which is 7, and we grant a very generous 50% of the rest of the parameters, the 50% is saying that 50% of what's left has this parameter. That's 193 different parameters. We get the probability of the universe having a habitable planet as 1, and 1 times 10 to the 51. That's a 1 with 51 zeros in front of it, and then the decimal place. Okay, 0.000000 51 times until we get to the 1, which is a very far cry from the 1 times 10 to the 17 stars found in the galaxy. In science, when probability of something extends beyond an exponent of 50, it's said to be impossible. So if we're at 1 times 10 to the 51st with a 1 over that, 1 over 1 times 10 to the 51st, life is not possible to have risen accidentally. It's such an infinitesimally small number that scientifically it's considered less than 0, because that 50 is the cutoff. And so we're at 51. We're 10 times less than the statistical 0 that we would need for it to even be possible. It's an amazingly complicated system that we live on, and it is very privileged because of the 200 parameters necessary for life. The likelihood of them existing anywhere else in the universe is tiny. Like it is so small. It's difficult for us to fathom with our finite minds. So Earth being a privileged planet is definitely one of those things that really makes the idea of random chance, something like evolution, being the cause for life to be here, to be super absurd, rather than to have been put here on purpose, with a purpose. And again, this is just looking at the science of it, and then once we look at the science of it, drawing the right conclusion. So I know it was a lot of numbers. I know it was a lot of math. Every one of those numbers can be verifiable. I don't really like going through all of the sources on these videos because they're already long enough, but I'm happy to provide them for anybody who really cares. Um, and I'm going to leave it there because that's just a lot of numbers. So thank you very much, and enjoy the rest of your day.